What's up? I'm Austin. I'm here with Carlos and Etta. This is day 4. Ooh, same shirt. Something weird must have happened. Day 4 of speedrun of the Web2 to Web3 curriculum. This is week 3, day 4. We're really getting through the speedrun now. We're really getting into some really cool details about building on chain and about kind of like the gotchas of building on Ethereum. This one is the dice game. So the dice game already exists, and you can basically roll the dice, and it uses block hash. So block hash is sort of pseudo random, but it's predictable. And we're going to get into why it's predictable here in a second. But what it does is basically you roll the dice by making a transaction, and then if the block hash is a certain number, you win, and if it's not a certain number, you lose. And I think it's just basically block hash, which is a really big number with like a modulus of 16 or something like that, right? Mod 16 or something like that. So we're looking from 0 to F. You're basically rolling a dice with 0 to F on it. And if you get a 0, maybe you get paid or something like that.
I think it's 0, 1, or 2, you get paid.
Okay. Interesting. We should it's weird to have a 16 die and then have 3 different numbers be the way. I don't know. We put this together quickly. It's a fun dice game though, but it can be exploited because what you can do, and here's the kind of the heart of the trick, is you put another contract over the top of it. And instead of you rolling the dice, it's your attacker contract that's rolling the dice. And you set it up so the attacker contract only pays to roll the dice if it's going to win. Now you'll make transactions to the attacker contract, and those transactions will check to see if you're going to win or not. And if you're not going to win, you still pay the gas, but you don't pay the fee to roll the dice. So you'll make multiple transactions where you're just burning gas, and what you're doing is just waiting for the dice roll to get right. And once it's one of the good rolls, then it will pay the full amount. It'll roll the dice, you'll win the money, and you'll be set. So maybe Carlos, you can show here. I'll share my screen real quick just to look through kind of the challenge here. Yeah, randomness is very tricky on a public deterministic blockchain, right? And what we're going to use the block hash, which is for now a result of proof of work, which is pretty darn good use of random, or a good source of randomness. But we're going to see why that's not the case as we get into this. And yeah, also soon we're going to see Randao stuff with proof of stake, which is interesting. We saw Damu create a future block hash using future block difficulty, doing a random. So block difficulty is going to be another source of random other than block hash, but we'll get into that another day. Today is all about rolling the dice. All right, so it looks like a player rolls the dice, they send in 0.002, and then there's, I think Zach wrote this, there's a 40% chance that the value is added to the current prize. He made a really interesting prize mechanic here where you can win like you win like 90% of the pot if you get one of those numbers. But I don't know, there's some interesting mechanics that he built into this. And this is the really cool thing about building smart contracts, is it's like, okay, we've got some randomness, we've got some dice. How do we want the, the reward structure to work? You as the developer can really get in and kind of like hack that together pretty easily by writing a few simple lines of code. So your job is to attack this dice contract. So you want to show us the dice contract, Carlos, and then maybe we can go with what the attack looks like. Okay, let me quit sharing. You show us that dice contract, and we can kind of dive in.
Yeah, I have to say that this is like my favorite challenge. I don't know, when you have to like break or hack something, I don't know, something with my brain that really wants to do it, so
the hacker anarchist just wants to drain the contract. Yeah. And I mean, when you think about when you're deploying a contract to Ethereum, you're deploying it for the rest of time, and for the rest of time everybody can get to it and attack it. So there's this really interesting thing where you have this small moment of time to make sure you get everything right, and then for the rest of time that thing is battle tested, right? So you really want to understand these attacks and understand like all the theory behind how these attacks work, so when you're creating smart contracts, you're not deploying something that can get attacked.
I think the first search that I made on Google when I was like starting with smart contract, how do I update a smart contract, code? That was like my first, like I make a mistake. How do I update the code? So long story short, you can't. You can't do it.
It's good to give that disclaimer.
There are upgrade patterns, but basically
yes.
it kind of breaks the idea of what, like, we want blockchains to be immutable. We want you to set up a small piece of code and people only have to trust the code and no one can change the code, and the code does exactly what it's supposed to do forever, right?
Yeah. It's like if you make like an NFT and the admin have a way to update like the hash or something, that's bad, you know, because you can do that if you want, but you don't really.
You might as well be
that.
using a database, and
yep,
it
will be cheaper. It will be cheaper and faster.
You don't need blockchain. If you want to just be in control of the thing and change it whenever you want, you don't need blockchain.
Yes. Okay, so can you see my screen?
Yep.
Yes.
Yep.
Okay, cool. So this is like the dice game contract. It basically is like super simple actually, because only have like one like main function, which is like the actual roll the dice. Yes. And well, I mean, maybe we can, this is like this is like an easy one. It's just, you have to pay 0.002 ETH to call this function. If not, it's going to revert. And I guess like this is like the interesting part of the contract. And this is how we are calculating like this random, like pseudo random number using like the block hash function. But this is actually interesting, right? Like it's taking the block number -1, right? So you are getting like the block hash of the previous mined block.
That's already there. It's already out in the public. Yeah.
Yes. So if you are already like reading this, you might be thinking, okay, see, if that block is already like mine, why can't like anyone like go there and do the same like calculation, right? Like, because you can go to the previous block and do like call the same function. And then we are like doing some encoding here with the previous hash, like the address of this contract and the nonce, right?
Think of that encode packed as just like concatenation.
Yes.
It's sticking the previous hash together with the address of the contract together with a nonce, just to get some really kind of random, like you want to get some unique randomness there. And that catch-hack 256 is just a hash function. So we stick the previous block hash, the address of the contract, and then some nonce all together, and then we hash that, and that gives us kind of like this sort of pseudo randomness.
Yeah, like the nonce is just like a number that you incremented like every one you call the dice.
I think your
voice is robotic.
Just move it away from your beard a little bit. It'll be good. You're good.
Is it good now?
Yep.
Yes.
No?
Yeah, you're good.
Okay. Sorry about that.
You're good. All good.
So I was saying that like the nonce is just like a number that you increment like every time that you call this function. So like is declared here starting with 0, and every time anyone call the roll the dice, just like increment it by 1.
Okay. We use the same method like for loogies, and we didn't put a nonce in. And if you minted 2 or 3 loogies in the same block, they all looked the same. So you could make, triplets, or you could make these loogies that looked exactly the same because there wasn't the nonce that was. So we had duplicates and triplets. Okay, go ahead. Sorry. Fun one.
No, that's fine. So then this is also like doing like this like modulus calculation, right? It's getting like converting the hash to a number and do like model like 16. And this is going to give us a number between 0 and 15, right? And then that's like give us like 16 options. And here we are saying, okay, if your roll is greater than 2, then just like return, like we are not doing anything. And if
money
not,
stays
like
in the contract.
you are like, yes, it stays in the contract, and the money stays here, like doesn't do anything else. But if it is like less than 2, I think it's 2 or less, like this code get executed, which is doing is just like sending like the amount of the price to you, right? Like to the winner, like the person that called like this contract. If they roll like 2 or less, you are getting like the price money back to you, right? Like this, remember like this weird way of like sending ETH, right? Like the message sender call, and we are calling like the empty function, and we are sending like this amount. right?
And with each
And also,
roll,
like, this is,
whether
like,
or not the roll fails or not, it looks like the prize money is incrementing. This is an interesting
Yes.
piece of state here. I think Zach must have done this. This is really interesting. So it's like it takes the like 40% of the money you put in and adds it to the pot.
Yes.
That's interesting.
Yes. Yes. And the other money, I guess, is like for future prices, right?
Yeah. Interesting. Cool. Okay. So how do we attack this thing? That's the next question, right? How do we get in here and only pay to roll if we're going to win? Or maybe should we go roll once or twice just in the UI just to see the thing go? Yeah.
Yeah. So this is like the initial UI that you get. So let's like the contract is already, like, the dice contract is already loaded with some money. So let's get some ETH here. This will be enough. So let's do like some rolls.
Shout out to Mr. D here for the artwork.
Yes. Yeah, very nice. So I rolled a 3.
It's got to be 2, right? Yeah.
Yes, right. 2 or less. Let's do it like a bunch.
We might be here for a while before we get a win.
yeah. But as you can see, like,
this is fun. I'd play this game.
Yeah.
Oh.
Yeah.
It's a fast
money.
Yeah, but the thing here is that we are like playing like peasants, right? Like we are like playing just like sending like money like every time, right?
And only 40% is going to the pot. I feel like this is a losing man's game here. Yes. Yes.
So yeah, like Austin said, like we should find a way to trick like this contract, right? And as we saw, the calculation, I mean, they are like actually like really simple if you look at it. So really what you have to do is like creating like this rigged roll contract, which is going to have basically the same logic, right? It's going to have like the same logic here. And here, like what will you do is you get the roll and you know that you want a 2 or less. So whenever you got that roll, you will let your contract, like your attacker contract, to call this contract, right? So let me, I mean, I don't want to show the code. So let's,
that's basically, you explained it. Basically, you want to do the same exact level of math. So you're going to do the same exact math twice, technically, in one line of execution, but you do that math outside in your attacker contract. And if and only if it's a winner, do you continue on and call the roll. One thing I wanted to look at, can we just see the console log? They're on line 29. There's this really nice console log of the roll. This is maybe good for debugging. Do you happen to have the hard hat node up? There it is. Yeah, we can see what the roll is. So you could be watching your hard hat node and know what it's rolling even before the front end even shows it.
Yeah.
Yep. But I think, I don't know how much even more we can show here. Basically, you kind of have to write the rigged roll yourself. And I'm not sure how much we can show of that without giving it away.
Yeah, I mean, but it's not really, I mean, maybe like the mechanic of deploying a contract and then you call that contract and the attacker contract is going to call this contract. That's tricky. But actually, like the inside the function, like the attacker roll the dice, it's just like maybe like copying this. It's like super easy because it's just, you just want to execute the same logic. And if the roll is good, then you call the contract. If not, you just can revert the transaction. And like Austin said, it's going to cost like a little bit of money because you have to pay some gas, for executing that function. But you don't need to send like the point like 002 ETH to the contract because you will only send that when the roll is good. So what I can do here, I have.
Can we do one rigged roll? Oh wait, yes. Go ahead.
Yeah, no, I have like this, like I have this commented out on my code. This is just like the UI button that calls the attacker contract. So if I refresh here, I should have the let's see. Yeah, it should be.
So do we have to deploy an attacker contract still, or is that deployed?
Yeah, that's already deployed.
Looks like it's already deployed. Cool.
Yeah.
Okay, so now instead of rolling the dice on the main contract, we're basically doing a rigged roll, which calls our attacker contract, and then that attacker contract does the same math and only calls the actual roll if that previous block hash looks like it's going to be a winner. Is that the right way to say it? So let's do some rigged rolls here and see how it looks.
Okay.
Basically, there'll be transactions where we're just going to spend. Do we need more ETH?
I think you need to pay 0.02.
Like we need ETH on the attacker contract, because the attacker contract is using its own ETH to send to the contract. Yeah.
Got it. And these are just things you'll have to debug as a a builder. You'll be like, why isn't this working? Think through it. Think through what's going on. Yeah. So here he's using the faucet to load up the rigged roll contract. So now when we call rigged roll, it will only make the roll. It will have enough ETH to send in to make the roll.
Yeah, and this is how I program my
interesting
my contract.
You just had it revert. Okay.
Yeah, maybe you don't need that really, but yeah, I think it's good just to see it there. So you can I don't know, you can call it like this like 1,000 times. Or maybe it's...
except for the nonce didn't move quick enough.
Okay, yeah.
So let's keep calling it, and then maybe we'll
get not
one
winning.
roll eventually. Yeah.
Not winning. Not lucky today. But this is good because I wanted to.
But if we were like doing a regular roll, then we'd be paying for all this as well.
Yeah, like this is
right. You're paying gas. Yeah.
You're paying some gas.
Yeah.
Yes.
Yep. Even for a failed transaction, you're paying that 21,000.
I mean, it's.
There it is. We got one.
Yes.
There we go. So we only paid that one time to roll. Very nice. Very nice.
And what I wanted to say that this is good if you want to test, like doing like a quick test, on the UI. I have to click it like 20 times. I don't know. But what I wanted you to look at is like the test, because the tests here are really interesting, like on this challenge, because we are like we spend like a lot of time like doing the test on the UI, and imagine if this was on Rinkeby on mainnet, right? Like you will be that like waiting like for 15 seconds or whatever, like every roll. So it will it can take long. So here on the test, you can see how the test do like an infinite loop to call, and it keeps calling the contract. I mean, it's doing like the same logic and only calling the contract whenever the roll is good. So you can also do yarn. I mean, you can do that in every challenge, I think. And every challenge we have like the test. So if you want to make sure that your contract is good, you can do like yarn test, and that will run the test against your contract. And it is also a really nice exercise, like just checking the code of the test.
But don't lean up against the yarn test as like you're not writing the code to get the tests to pass. Like write the code to understand what you're building, and just have the yarn test be some validation at the end.
Yes. So here you go. Like
awesome.
The 6 tests are passing. We did like the test on the UI, so everything should be good to go.
Great. So public deterministic blockchains are really bad at giving you random numbers, and those random numbers are predictable, and they're sort of like tricky predictable, where you have to kind of still have a kind of contract on chain that's predicting it and going to check it. And for us, we're just like kind of jamming those transactions and hoping they'll go through. But that's it. That's challenge 3, the dice game. Go exploit the dice game and set up an attacker contract so it only sends value into that dice contract if the block hash and everything are aligned for you to win. Good challenge. Go ahead, Carlos.
So no, I wanted to say that like an open question here, like what would be like if I really want to make like a dice game on blockchain, what would be like some like good alternatives to this? Because like, as we saw, like this is not really good, like everyone is going, not everyone, but some people will steal our money and will always win. So what are like some good alternatives? So what are like the best options?
Good question.
Yeah.
So like for randomness, there's this pattern called commit reveal, where you commit a hash of something and then later on you reveal the something and it proves that it hashes to that, and then you hash that with block hash or something like that. There's also VRF, which is from Chainlink, which is an oracle where you can ask for a random number, and then sometime later they'll call into a callback function in your smart contract giving you that randomness. And there's block hash and there's block difficulty and a couple other things, but those are kind of the key ones that you can get. Am I missing any? So there's like block hash, right? Which is what we're using here, which is the least amount. Then there's commit reveal or VRF. VRF is more expensive. Commit reveal is expensive in terms of user experience. Your user has to kind of like save something and have it to commit later. And if the power goes out and their laptop dies and that's only sitting in memory, then that commit reveal breaks, right?
Yeah, so I think we have a nice build in the build kit, right? Like this rock, paper, scissors commit reveal pattern. I mean, that's like a good build to check if you want to know how it works.
And there's a VRF NFT also showing you how you can get randomness for your NFTs. And that's one, like the block hash works pretty well for NFT randomness if it's not like a super popular NFT that people are going to write a attacker contract for. Like if we just were minting today and we're only going to mint 100 of them for the next 24 hours, probably no one's going to build an attacker contract in that much time for some little NFT. So you can get away with it sometimes for little things. But yeah, if it's a long running thing and it uses previous block hash, it's going to get attacked. Okay, awesome. That's challenge 3. It's a dice game. Go exploit it. Carlos, Etta, hearts, hearts, hearts. Thanks for hanging out. See you guys for the next one.
See you. Bye.
Bye, everyone.